Welcome to this workshop on the use of neural networks for property estimation. In this workshop, we'll examine the steps needed to create and configure and commission a neural network for estimation of a quality parameter associated with a process. In this workshop, we'll be using a continuous digester as the example in which we're estimating the kappa number. In the first part of the workshop, we'll be looking at how the application is configured, and then we'll move on to looking at how then data associated with the process is used to train the neural network for property estimation. We'll be looking at some of the tools included in such applications to validate the model before you apply this online. Then we'll be looking at the model being implemented online in the simulated process. For this workshop then, this continuous digester we're using is typical of what would be used in the pulping industry and pulp and paper manufacturing. Chips are put into the continuous digester, go through a steaming vessel, through a high pressure feeder, and then are carried by liquid into the top of the K-Mir digester. White liquor, which is a caustic, is then added. So the addition of the caustic plus the fact that the liquid is then heated to a very high temperature causes the delignification of the process to occur, which frees the cellulose. The cold blow flow acts as a wash flow, which washes some of the lignin that was delignified from the pulp. The pulp then exits the digester. The degree of delignification is indicated by the kappa number analysis. You can have an online analyzer, but often these are maintenance problems. So we're, in this application, saying we're going to have a neural network as a check on our analyzer online. So our analysis coming in that we'll be using in our module is a measurement from that analyzer. The neural network is configured by applying a neural network block within the module. If we had been using a lab entry rather than an online analyzer as the estimated property that the neural network work with, we would apply then the lab entry block. It wouldn't really change the way we configure the neural net application. Configuration is fairly easy. You're just basically having to identify the upstream parameters that are impacting operating conditions that are impacting the kappa that's produced. You can apply a user-friendly name to each of the parameters that are used. This will be used later in the application. Also, as part of configuration, it's important to say how often information is to be archived. In this particular case, we're running the simulation much faster in real time, so we're sampling it once a second. This is pretty much what is required to configure the application. Once that's done, then the module is just downloaded, and the parameters that are used are automatically assigned to your historian. So when you open the neural net application, those parameters that you configured are automatically shown with their user-friendly name, and the historic values of those are then shown on your trend above. In creating a property estimation, then you're using historical data to train a neural network to do this estimation online. The only thing you have to really apply or define is the time to steady state. That is how long it takes for the process to respond to these input changes. Up in our trend area, we just by right-clicking, we can define a green area which says this is the normal operation where the process is operating over normal operating conditions. If we have an area where the process was shut down, we can add an exclusion area. So in this way, we can select the data used in training and also screen the data very easily. Once we've identified the information to be used, we just then do a sensitivity analysis. The sensitivity analysis, we're doing a cross-correlation between the lab or the predicted parameter that we're measuring, in this case the online analyzer, and the parameter By doing a cross-correlation, we can determine the delay associated with an input change and its impact on that value that we're going to be predicting. So in this case, you notice there's quite a bit of delay between the input changing and its impact on kappa number. So this is automatically done for you. The relative amplitude is indicated by the bar in terms of the impact upon the quality for a change. We can then, once we have confirmed the delays, we can then train the neural network. There's some options available. One of the key options is how much data we want to set aside to be used in testing the network versus training the network. And normally that's a 20-80 split. Just by saying train, then we automatically go through and determine the number of hidden nodes that would be required in the neural network to get best estimation of the kappa. So this is automatically done. Also, the point at which we're overtraining, we stop that. We determine that by comparing prediction or the training of the network using test data versus the training data. Once we have created the neural network, then we can see how good our model is by doing a verification. In this, we're comparing the actual value versus the predictive value for the data over which we were training. In this case, you see we have a very good model. We can look at it in a couple of different ways, as is shown here. So through the verification method, we can then have good confidence the model is going to work well online. Also, the R-squared and error squared parameters are an indication of the quality of our model. Once we're satisfied that the model is correct, we can then go to our module. And the actual model has now been put into the neural network block in the configuration database. So by downloading our module, we're actually putting the neural network online and running in the module within the controller. So by having it in the controller, it's a very secure environment where it's running independent of the workstations. So once we have downloaded our module, we can then go online and view the module running in the controller in this application. So in this particular case, we notice that we're now predicting what the analyzer would be providing. And so by comparing those two, it's a good cross-check. There's also a future which says this is the value that the kappa will be if the current input values remain where they are. So this can be really a helpful value in setting up a digester on a throughput or grade change. I hope this has been useful to you in seeing how this is done.